Right another last word.
Okay, I see something is handwritten.
Just one, problem one.
Okay.
Oh, don't look too close. You might be disappointed.
No, I'm impressed. I'm impressed. At least I see a proof that you can read. Open source, and you placed here the commutation relations for angular momentum. You, as a, at least you will be well prepared for next chapter. Perfect. Okay. Okay, but much appreciated. Oh, impressive. I didn't exceeds expectations. Well, it's not the way the whole this practice exam was designed is a little excessive, but strong. You took thermodynamics in the past. I see it from the style how you solve the problem. Mm-hmm. Did you took physical chemistry before
No,
or something similar?
I had someone else help me also.
Okay, yeah. I see a hand of a person who took physical chemistry in the past. Oh, it is probably above the. It was not an undergrad. It was either a graduate student or undergrad from physics. You don't need to disclose the name, but is it?
It was a graduate from physics.
Okay. Okay, you have good helpers. I will just quickly look. Huh? You will be the last but not least.
That's fine.
Thank you. Okay. Yeah, thank you for your effort. It's really appreciated. So let's we'll have some administrative discussions, and then we need to attempt to complete oscillator, so that we go into the angular momentum that I see you maybe not love, but at least acquainted with as soon as possible. So here is what I've got as your responses. So there are three people who explicitly like have a final exam in the form of solving problems. I give full respect to these brave people. Well, you need to collect 2 votes more to be in majority, because if you do different things, it's different. So if you do not collect 2 votes more to do an exam, then you'll probably go with projects. And after this practice exam, I hope you wouldn't mind. You can come in person. I will follow the votes and whatever is reasonable, and delegate my effort. So probably we cannot decline projects at all, even if you do exam, and you'll do so the choice is what we do on the day of exam, like making 5 minutes presentations of the Hello, Fanny, how are you?
Thank you.
Yes. So, I'm very happy to see it. So, I will return to this stuff shortly. But I want to give an immediate feedback on the homework problem. So, there were two attendees of this class. There are no secrets. I'm not hiding the names. Who were brave enough to look for this Frank-Condon problem of looking populations of 15 levels of harmonic oscillator, which is shifted. We will work and do this problem in class in maybe like 2 or 3 lectures before the end of semester. I really appreciate that those who completed this assignment understood the question and did great effort. But there is, just for your curiosity, there is an important thing. I see that those who are already exposed to thermodynamics and statistical mechanics think and believe in Boltzmann distribution that lowest energy level is populated as at most. And then as you go higher up, it is less and less populated. This is a very cool thing. It is correct for a system in a thermal equilibrium, which is 99% of things that happen in the world, including the sun, which is black body radiation, blah, 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 right? Also, it is not black, but it is black body radiation formula. But the question was either I mentioned explicitly coherent state or mentioned that the oscillators are displaced. And if we promote in molecular spectroscopy the wave packet of the ground state into the excited, it creates a shifted. It will be a quantum state corresponding to what we covered today in lecture, so-called coherent state or eigen state of annihilation operator. And there, as we may not remember from previous meetings, the expansion coefficients and populations, they not necessarily decline as we go up. They first grow and then decline. And this coherent state population distribution is different from Boltzmann. So it is. So the Glauber got his Nobel Prize not for nothing. So he found that there are states that differ from Boltzmann distribution. But I saw a fair effort to address it and give an answer which is very natural in the natural phenomenon. Okay. There are 3 people who do not like projects and like exams. But if you want to do exams like this on the final week seriously, find at least 2 people more to have a full consensus. But we will do projects without presentations, just a written report of 10 pages or whatever. The course is organized this way. Probably you feel discomfort. Well, I understand your major discomfort is not about the projects, but about presenting in front of unbiased audience. Especially Dr. Rasmussen and Dr. Rogers. If I would promise that they will not come, probably you will immediately vote for projects. And they may not come. It will be just open invitation, whoever wants to come. But please, I already recorded those who like exams, but please, everyone, even if you like exams, select a subject. And if you're not sure what to select, do not hesitate to approach me. I have much more ideas that I can do myself. So it is preferably that you do what you like, but if you are not sure, you can consult by email or in person. And it is the most beautiful part of academic life. All natural sciences disciplines are targeted for human curiosity to do research. Without research, it's the material same as Latin language. So if we do not apply it to anything new, then it's it's nothing. So it's very respected attitude to try to do any research, and it is preparation to a future career. Even if you are not going into academia and R&D and industry, it's still part of this. Since you selected this general path in your career, it is related to what you do. And for the way how it was in previous years, I'm just projecting the things I observed as a student myself. When there is a didactic academic material, my instructors were like hard on everyone. But if a person expresses an interest to do something independent, a lot of errors are forgiven, just fast. Okay. So I can talk for hours about each of these projects. It's or design something new. So do not hesitate if you're not or if you do not have enough information to make your decision. Okay, so if the stars come into right order, in 35 minutes we should arrive to these two equations. If not, we will briefly continue next time. So, what where we are and what do we do? We did spend time into finding eigen states of the annihilation operator, and we found two things that there is a recursion. There is a specific way how they progress, and they didn't comment it sufficiently in sufficient detail. So, if you look on each of these terms, if you put as function of n, you can see that there is a power in the nominator, and there is a factorial in the denominator. So when the eigenvalue mu is small, less than 1, then each element will become smaller and smaller. Same as in the Boltzmann distribution. The population meaning of this C sub n absolute value squared is population of the level. And if eigenvalue mu is smaller than 1 dimensional stuff, then as we go to higher and higher and higher, we have less and less population. But if the mu is larger than 1, then the progression of the power, here's n equals 1, n equals 2, n equals 3, and it gives growth of population as we go to more and more excited to a certain limit. And then after a certain limit, it will start to decline. So there is a certain quantum level that has a maximum of population. It is a very interesting observation, and it has its reflection in the molecular spectroscopy. If you do atomic spectroscopy, there are lines, and there are plans we will cover it in the lectures. So just linear spectra, emission or absorption. If there are molecules, they have shapes, and it is not just homogeneous broadening from the line up and down. It is unsymmetric shapes with a little sub-peaks corresponding to individual vibration transitions. And these features of molecular spectroscopy are tightly connected to this distribution. So this coherent state is not only crazy people who want to see time dependence, it also gives the regular static spectroscopy predictions. Okay, so we got this stuff, and we also discussed that the attempt to solve time-dependent Schrödinger equation with coherent state with eigenstate of annihilation operator as initial condition will give us some propagation, accumulation of phase, and one can combine together expansion coefficient and accumulation of a phase, right? If we do this trick, we can look on this problem as if eigenvalue accumulates phase. And then if you practice if you look on it as series expansion, we see that power is just a really great luck for harmonic oscillator. The base of phase accumulation, which is I omega times n times t, right? And the power in this coherent state, which is mu to the power n, has the same power, and we can combine them and tell that it is a mu to the times e to the power I omega t is a new modified eigenvalue which accumulates phase with a frequency omega t. So this is a main conclusion from discrete space consideration. Yeah, I think it's this slide. So we do have coherent state expansion, and our expansion coefficients are time dependent with this eigenvalue of annihilation operator oscillates, which is quite unique. Most of other eigenvalue problems give static time-independent eigenvalues. Now, what we are going to do today, we are going to borrow the information about time-dependent eigenvalue. And then, with knowing this eigenvalue of annihilation operator, we are going to redo the whole problem, but in the continuous space, as we typically do in calculus and differential equations. Why are we doing it? What I'm going to get is Gaussian distribution, which is shifted from the equilibrium. And shift of the equilibrium will be connected to this eigenvalue, and then we'll see that shift from the equilibrium will be harmonically oscillating. So I'm playing open cards. You already know the answer. Now we just need to have a little effort to do steps. Okay. It's before we go to equations, I want to focus your attention on this ugly image, but it does relate to molecular spectroscopy, and it does relate to the question of populations, like why coherent states are relevant to everyday life, why it is not exotic, why it is not only femtosecond expensive experiments. So in molecules, the energies of electronic states, there are enthusiasts who like abbreviations HOM and LUM. Okay? And there are also LUM of +1. Right? So the energies of electronic states are not static. In atoms, they are what they are. In molecules, if you expand or contract interatomic distance, the energy of electronic state will be different. And it gives potential energy surfaces. So in ground state, we have one potential energy surface, response of a system to elongation and contraction. But if you go to excited, it will be different. And this is typically symbolized by figures like this. So there are one potential energy surface in ground, another in excited. Maybe there are dissociative potential, multiple things. So if the equilibrium points of ground and excited do not coincide, it means an excitation of a molecule by light in a regular spectroscopy experiment means that the wave packet distribution for the ground electronic state is immediately projected into excited potential energy surface. But for excited potential energy surface, it is not at the equilibrium. So it is a shifted Gaussian distribution, which will immediately feel the force downhill, and it will start oscillating. So it is a connection between our boring abstract exercises and real life. So to create coherent oscillating state, you just excite any molecule by a short laser pulse. If you do not have short laser pulse, if you do just CW excitation, it's still vertical transition. And then it will be different individual vibronic levels of the excited state that will absorb different portion of this one. And the distribution of the vibronic states in the excited state potential surface will be the same as for coherent state of the displaced oscillator. So it is a reason why absorption spectra have this vibronic profile. I plan to dedicate the whole full 50 minutes, generous 50 minutes lecture, maybe -3 from the end, to the subject. I used a textbook to for annotations. Therefore, there are this crazy values sigma and gamma. I will address them, but the meanings of this sigma and gamma is similar to the mu. I will speak about it. So strategic planning is done. Now you can lean back and relax. I'll tell you when there will be something strategically important. In the past, we did found the eigen, or the ground state of harmonic oscillator by trying to jump lower than the basement, by applying annihilation operator to the ground state. We used to have the equation which is very similar to what we have in the top line, but we on the right side we had 0. Annihilation to wave function equals 0. Now we have the same wave function on the left and right and the eigenvalue. I do conversion between gamma and mu due to a textbook, and send you the stuff so that you follow how good I reproduce the text, if you're interested. Now, we do have the annihilation operator as a superposition of position and momentum. Position is position, momentum is a derivative of space. So we are going to apply, to practice it as a differential equation. And under gamma, we will, instead of, under gamma, we will assume this time-dependent eigenvalue, which accumulates phase with frequency omega. Okay. So the sigma is a conversion factor. We do need to focus on the differential operator, and it is a natural intention to practice laziness and minimize rewriting the fundamental constants over and over again. So if we take the definition of the annihilation operator and just combine things that one can cancel, then one can identify that for the position, we will have the Planck constant in the denominator of square root and mass and frequency in the nominator. If you look for momentum, it will be an inverted thing. We will have the Planck constant at the nominator and mass and frequency at the denominator. So it looks like the factors in front of position and momentum are inverted in respect to each other. Okay. And then we can call it as sigma and express the annihilation operator in terms of this sigma coefficient. The meaning of the sigma is natural width of the ground state, right? It is what would come this combination of Planck constant, frequency, and mass it determines how broad or narrow the vector is. Okay. Yes,
Can you go back one?
yes. Extra credit for any found error.
In the bottom picture, wouldn't it be 1 over the square root of 2 times 1 over sigma?
1 over square root of 2. Yes. I don't know who got +2 in previous years. Maybe there is one more error here. You may have it, yeah, in a more legitimate writing. So let's see if I will not do corrections because we need the in principle answer. So do we approve the So does the top equation make sense? Except little factors. If you are in doubt, let me know. Okay, so annihilation operator is position and momentum, right? And we do have an unknown function, and here we do have the oscillating eigenvalue. So what do you do if you need to solve this equation as a active takers of the differential equations? Do you see any challenge or it is a straightforward thing? So we can multiply left and right by increment of the independent variable, right? And we also can divide left and right by the unknown function. Why are we doing it? Because there is a temptation to have left and right parts of the equation depending on only one type of variables. So to have everything related to independent variable on one side and everything related to unknown function on the other. So if we divide by dx and by psi, right? Then the central part will be depending only on the function, and first and last term will depend only on the independent variable. And we do remember that if eigenvalue will be 0, if you have no right part here, we would reproduce ground state of those three. So we may want to move the things related to independent variable on one side. Right? I should have more legitimate writing. Yep. So then on the left, we do have increment of the unknown function over the unknown function, which is what? It's written here, but someone can verbalize it. Integral dx over x equals. Okay, it is what we get here, right? And then on the right, you have x dx, which is polynomial, right? Square root over 2, and here dx is just x. So on the left side, we have a natural log. Why does one put psi naught here in the denominator? Is it natural to put constant in the denominator of natural log, or you're not sure? Yes, no, unsure.
If you're integrating over an interval, right?
Mm-hmm.
So then you end up with natural log psi minus natural log psi naught. So that you can combine them.
Yes, thank God. So, everyone who understood, or we need him to repeat and teach us more? Okay. So, Garrett told intervals. Another way to think about it, that indefinite integrals need to have free integration constant. And our freedom to select integration constant as a log of something, and then subtraction of two logs will put the stuff in the denominator. So we just select things in the most comfortable way for us humans because of mathematical ability. And then on the then we can plug in left and right side, again by mathematical liberty, into, you can do the same mathematical operation. For example, you can put left and right side to the power of exponential and still keep the equality, right? So here I'm just running ahead of the train. So psi over psi naught, right, on the left, and then exponential to the power of this polynomial. What is important, we inherited this minus sign because we were, I apologize, I'm going backwards. So when we were moving from left to the right, we inherit the negative sign, right? And when we go forward, here is this negative sign, right? Here and there. And then exponential to the power of this result of integration looks very much like, starts with letter G and shown in German money. Gaussian, yes. But we feel comfortable to have Gaussian centered at 0. And here we have an additional polynomial term. What do you think about it? What do we want to do? Just for our personal mathematical comfort. So here is my train of thought. We have e minus x squared plus x. But I always like to have centered Gaussian. Is there a way to convert from top equation to bottom equation? Would it be a little more comfortable and easier to analyze? Aidan? What do you think? Come on. Oh, okay, yeah. Thinking is respected and sacred activity. Let's take your time. Okay, so do you think it would be beneficial to convert into this shape? And I'm practicing laziness and skipping this, blah, 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 just generally. Okay? So how can we go through a polynomial polynomial to full square.
Square.
Yes, excellent. So, and by practicing mathematical liberty, we can always add and subtract missing term, right? So, if we want to consider the stuff here as a squared, then we need to consider this one like 2 a squared a b squared, and then we need to identify what would be our b to practice a minus b squared blah blah blah, right? So then our b likely will be related to gamma. Probably need to do it. Yes. I don't help myself. I need to do this. And then there's all this exercise. Learned how to breathe. I'm just fine. So let's do that. So minus 1/4 x squared over sigma squared. Plus gamma x over sigma. So I probably can denote x over 2 sigma as a, right? Then if I want to see here 2, then times x over 2 sigma times gamma. This is my a. This 2 comes from standard equation, and gamma will serve as b, right? So, and I need minus sign because they have opposite sign. I can put minus outside of the brackets. And then I need to have plus b squared and minus b squared, which will be just plus gamma squared minus gamma squared. Okay. Then this combination will give me a minus b squared, which will translate in this situation as x over 2 sigma minus gamma squared. And we inherit the minus sign from here. And then if we practice this minus sign outside, then we need to flip sign in here. I can do it this way. Minus gamma squared. with our this stuff. Feel free to report any errors that you see. If you don't, or if you just approve general direction, this. So we can tell that our wave function of position and time will have the shape of this Gaussian exponential, and we know that gamma is time dependent. But again, by practicing mathematical liberty, we can just bar tilde and tell that initial we'll just see now. We do have a normalization constant that would include this gamma if it was just time-dependent normalization constant. And if one needs, one can always put it just normalization, whatever it needs to be, times this E minus gamma squared. And then the rest will be just Gaussian function, minus x over 2c minus gamma squared. So we got the wave function as function of time. If we would be mathematicians, it will be sufficient. But for natural sciences, it is not enough because wave function is not unobservable. We need to go either for interpretive work over probability distribution, or we need to use this wave function to find expectation of values of reasonable variables. Probably let's go to probability distribution in the remaining time. So this notation, originally we had mu. If you do not like this notation, I can give authors of the text who should be responsible for this. It's just notation is not ideal, but then derivation becomes shorter. And the authors who are responsible for this are George Schatz, Mark Breitner. The book is Quantum Mechanics and Chemistry, and Squires, not Squire, but Squires, Problems and Solutions in Quantum Mechanics. By request, I'll send. Oh, I will not send. I may send by error. And just to make a couple of lines derivation shorter, they tell that phase accumulation always has omega t factor, but to be general, one can have initial phase. And the initial phase, which is time independent, but they want to call everything except imaginary unit as a theta. Okay. Then if we need to analyze probability distribution, we need to take wave function conjugated and wave function non-conjugated and multiply. So here are quite unreadable and ugly calligraphy of this idea. So we have wave function conjugated times wave function non-conjugated and pure probability distribution. The original expression that one needs to practice, and here to follow this authors, I slightly step back before identification of a full square. We have quadratic term and the term that combines both eigenvalue and independent variable. If we do it with and without conjugation, one of these eigenvalues must be conjugated. And if we perform this multiplication, we will have the quadratic term Q has twice as bigger because of the square, and a term that would correspond to eigenvalue with and without conjugation. Okay, so would you approve this little trick? Yes? If you're not sure, let me know. Yes, no? Just multiplying by function conjugated, everything is the same except the eigenvalues, which do have imaginary unit, and you need to carefully practice conjugation. Now, if we add together this eigenvalue of conjugation later with and without conjugation, we do have this theta, we represent it in a form of imaginary exponential, and theta comes with plus and minus. Adding together exponential with imaginary exponential with plus and minus refers to our old body Euler, right? So it will be cosine. So and theta in here will be our initial phase minus omega t. So you have the square term and the term which determines shift of the center of the oscillator, or the parameter of the shift, so everything except x, oscillates as a cosine of this frequency omega t. Right? So you already feel more or less convinced. The center of the Gaussian distribution will be shifted. The shift is dynamical, harmonic, and the value of the shift goes as cosine of the main frequency of the oscillator. So it will be a Gaussian function that goes forwards and backwards. Then one can redo it carefully, identify full square, right? And report the answer. That the probability distribution will have the Gaussian functions shifted with dynamic harmonic shift, and there will be additional term which, by mathematical liberty, we will reassign to normalization factor. So if one carefully proves this normalization factor, and we call this independent shift as x naught over t, then one will arrive to a standard Gaussian shape for distribution, and it is what we were repeatedly obtaining in the evening Wednesday MATLAB exercises. So, I'm not sure if this part was recorded with the image, but I'm asking you to give me a favor and symbolize end of the, yes, thank you. Meeting is dismissed. Everyone is welcome to adjourn. Depart.
Disappear.
Disappear, yes. Selection of the mini project subject.
What are we voting for?
What? Please. So by now we have 4 people who selected the sports. So each one, please select the subject of mini research that you like it most, that you hate it. Okay. You have a preferred project. Okay, yes, yeah, thank you. John, you prefer?